Hi girls, and welcome to another Redox video. Today we're going to be looking at how we can write down what's happening in an electrochemical cell using what we call standard cell notation. So, our electrochemical cells consist of two half cells. One half cell which is being oxidized and the other half cell which is being reduced. Now, it's really important when we do these to know exactly which ones are being oxidized, which ones are being reduced, and to write it in such a way that anybody can look at it very clearly and see exactly what's happening. That's where the standard notation comes into it, and this is one of those standard chemistry conventions that we expect you to be able to use in your assessments. So what does it look like? Well, if we imagine the zinc and copper cell that I made in class the other day, where we had zinc turning into zinc ions in one reaction and copper ions turning into copper metal in the other reaction. We would write that in this way. And what you see here on the left-hand side of that double slash, we've got the zinc metal turning into zinc ions. On the right-hand side of that double slash, we've got the copper ions turning into copper metal. So the left-hand side of this is always representing the oxidation reaction, and it always shows it in order from left to right as reactants to products. So oxidation reactant, oxidation product, then we go reductant reaction or reduction reactant, reduction product. Finally, we have the double line in the middle, which is what's representing the salt bridge. So we've got oxidation reaction, salt bridge, reduction reaction, ultimately. So when we're writing these, there's a few rules to remember. First one, most important, is oxidation's on the left and reduction is on the right. R for reduction, R for right. Useful way to remember it. The double line always sits in the middle, and that is the salt bridge. Now, where you have a reactant and a product, either in the oxidation or the reduction reaction, where the species have two different states, so such as a solid and an aqueous solution, or an aqueous solution and a gas, or a solid and a gas, or whatever, then we use a single line to separate those two species. If they are both in the same state, we've got two gases or two aqueous solutions or whatever, then we would use a comma to separate them. If we have aqueous or gas, things that we can't connect electrodes to, then we need to use an inert electrode, usually platinum or carbon, that's graphite, and this is usually shown on the outside of the cell notation, or sometimes called a cell diagram. So let's show you a couple more examples. This one here, the oxidation reaction, shows iron metal being oxidized to form Fe2 plus ions. The reduction reaction has hydrogen ions being reduced to form hydrogen gas. Now, the left-hand side of the cell notation is exactly the same as it was for the zinc one, except obviously it's for iron. The right-hand side is slightly different because we've got hydrogen, which is hydrogen ions, which are an aqueous solution, hydrogen gas, which is obviously a gas. Neither of those are things that we can connect an electrode to, so we need to have an inert electrode in there, and that's why the platinum is sitting out to the side. Because all three species are in different states, so the hydrogen ions, the hydrogen gas, and the platinum are all different states, they are all separated by those solid lines. And of course we've got a salt bridge between the two of them. Second example, slightly different. This time in the oxidation reaction, we've got vanadium 2 plus ions being oxidized to form vanadium 3 plus ions. These are both aqueous solutions, so in this case the two species are separated by a comma, not a slash, because they're the same state. But again, they're aqueous, so we can't connect an electrode directly to it, so we need to add an inert electrode. In this case we've got a graphite electrode. Graphite is carbon, so that's shown out to the side. If in doubt, you should be told what your inert electrode is. If you're not sure, it doesn't really matter whether you use graphite or graphite or platinum. But in a laboratory situation, I can promise you that at school we cannot afford platinum electrodes. It would be really cool if we could, but if we could afford platinum electrodes, then I think it would be a very different kind of skill. Anyway, that's just a slight aside. Back to this example, so we've got vanadium 2+ being oxidized to vanadium 3+ in the oxidation half cell. In the reduction half cell, it's much more standard, and we've got silver ions being reduced to form silver metal. And there's really nothing that I can say about that. However, one of the questions that inevitably comes up is, how do I know, given that we've got both the oxidized and the reduced species in each half cell, how do you know which one's actually being oxidized and which one's actually being reduced? And that's where we need to look at our standard reduction potentials. Standard reduction potentials are a way of measuring how likely a species is to be oxidized or reduced, simply put. Okay, so these are all done relative to a hydrogen half cell, which is the hydrogen ions to hydrogen gas platinum electrode. You can look up reduction potentials anywhere you go. They are on the internet. They're in every chemistry textbook you'll ever come across. The key thing is that these are standard reduction potentials, so they are calculated under standard conditions. Standard conditions mean we have aqueous solutions at a concentration of 1 mole per litre, a temperature of 25 degrees C, and a pressure of 1 atmosphere. So that is always standard conditions. If it's not being done at standard conditions, you won't get quite the exact same answer. Now, these standard reduction potential tables, they all look like variations of something like this. They are listed in order of strongest oxidant to weakest oxidant, and they are all written as reduction half equations. That is the standard convention. Doesn't mean every reaction is a reduction reaction, just means the oxidation reaction is the reverse of the reduction reaction. But they're all written as reduction reactions, and all the potentials are given for those reduction reactions. So you'll see the right-hand column there at the top, it says E0, the little naught in a circle, that means standard conditions, and it's a voltage measurement. So what this is telling us is that relative to hydrogen, if I have a fluorine half cell and a hydrogen half cell, the fluorine is a stronger oxidant than hydrogen, so it is more likely to be oxidized than hydrogen. Sorry, more likely to be reduced than hydrogen. I'm obviously getting a bit tired. So the fluorine would be reduced to form fluoride, hydrogen gas would be oxidized to form hydrogen ions. And when we match those two up, the fluorine has a higher voltage than the hydrogen by 2.87 volts. Really, the voltage is a way of measuring the relative strengths of these oxidants and reductants. So the more positive the voltage is, the stronger oxidizing agent, the stronger oxidant the substance is, and the more likely it is to be reduced. The more negative the standard reduction potential is, the more likely the substance is, the product effectively, is to be oxidized. So the more likely it is that the reverse reaction will take place. So when you're comparing any two half cells, you know, if I've told I've got a permanganate half cell and a bromine half cell, the one that is more positive is the one that has a more positive voltage, is the one that's going to be reduced, and the one that has a more negative voltage is the one that's going to be oxidized every single time. The one that is more negative is going to be the oxidation reaction. The one that is more positive is going to be the reduction reaction. And for the oxidation reaction, all we need to do is to reverse that equation. So for example, if we look down at zinc, the oxidation of zinc is zinc metal turning into zinc ions. The reduction is zinc ions turning into zinc metal. It's the same reaction backwards and forwards. Okay, so ultimately, we use our standard reduction potentials for two purposes. The first one is to actually figure out which one is going to be oxidized and which one is going to be reduced. And in that, we're looking at the one that has the more positive standard reduction potential will be reduced, and the one that has the more negative standard reduction potential will be oxidized. The other thing that we use these standard reduction potentials for, which I'm going to talk about in my next video, is determining exactly what voltage you can expect from your electrochemical cell. And that will be my next video. I'll look forward to seeing you all there. Thanks, girls. Bye.